Try to stay on time. So hello everyone. My name is Morgan. I'm a postdoc at the Technical University of Denmark, and I used to be a PhD student at ANSTA, so I know some of the people here. Today I'm going to talk about, so as Juliette introduced, this long title. It's more about, let's say, ships, so on the surface, but I think the framework I'm going to present you can still be related to robots, and especially groups of robots. So this is a sum up of the work I've done this winter, mainly simulation and theoretical, but I'll introduce a bit what we're going to do with the experiments. I'm not going to come to Brest because that's too much equipment to transfer, but I'll be looking at what you guys produced this year. So the context of what I'm working on is about remote pilotage, where so it involves humans. It's not fully autonomous. It usually human pilots have to board the ships to guide the crew through the waterways or within the harbors. And the project I'm in is trying to enable the capability of doing it remotely, like an air traffic controller, where the human pilot stays on land and guide the ship with the crew from the distance. That's what our partner DenPilot is trying to implement for different business perspectives. This creates a technical challenge, however, in the form of the pilot now needs to rely on external sensor to perceive the environment of the ship as the person is no longer on the ship. And this creates a risk of the human pilot and the human crew of having different views of the reality, which then creates some communication issues and eventually some accidents may happen. More specifically, what I'm working on in this project is to wonder if we can use existing data fusion pipelines to evaluate the reliability of the data in real time. The challenge is that this data is multimodal, so it's the sum of different type of sensors being present on different type of platforms, and they are also moving, so they're not always seeing the same areas. They have their own field of views. And my challenge is to come with some sort of general frameworks to see how well we could evaluate the reliability of the data. When I say reliability, the notion is quite abstract in general, and I haven't really defined it properly yet. It's more a notion of we expect the data produced by the sensor to match the quality and uncertainty that we are expecting from the sensor. And today I'm just going to talk about the use case with multi-object tracking. So we'll have sensors producing tracks of objects around the ship, and we'll just fuse these tracks to evaluate how good these different sensors are at tracking the surrounding objects. Just a bit of feedback, or background on what I'm meant by multi-object tracking. One of the common methods for this is that the modalities, when I say modalities, I mean a group of sensors, like a GNSS, a radar, and an IMU to know the position of the ship and then the position of the surrounding. There exist a lot of filters, and some of them, it's quite common that they output some Gaussian components. So they would output a sum of Gaussian components that all have a midpoint and a covariance matrix such that you can represent them with confidence ellipsoids and some existent weights. They also exist some fusion methods, such as this one, which is quite simple. You just have a threshold and distance, and you use the Mahalanobis distance, which consider the covariance to be in. which helps us to decide if two Gaussian components will match or not match. And sometimes when they overlap a little bit, this is where we have to tune the threshold for the matching. Right. So I'll assume these two last slides will be the input of our situation, and we'll have something like this. So you have different sensors. They could also be on robots if you had robots, and they're all doing object detections, object tracking, and producing these intensities. Now I have already this method of fusion between the Gaussian components, but for now it's just say if they match or if they don't match. So based on that, I work on this right part of the figure on being able to fuse these tracks and give some levels of diagnosis. I'll go in detail about this in the next slide. So the first block, distributed MOT fusion, we decided to go for a distributed approach on the fusion because we have no ground truth. And we want the system to be quite modular to add and remove sensors when possible. So this block will evaluate some relative trust between two sensors. Like camera 1 will evaluate the reliability of camera 2. Camera 2 will evaluate the reliability of radar 1, etc. And then there's 3 diagnosis blocks where we make an average on these relative trust. We add some biases in these averages such that the output of the average has some practical meaning, as I'll show in the simulation. One of the sub-challenge I had when comparing two sensors was to decide what do I measure to evaluate if things are going well or if things are not reliable the way they should be. And one of the metrics we eventually picked up to evaluate the trust between two sensors is the proportion of overtracks, where we count the number of Gaussian components that are in the intersection of the monitored area but are unmatched. So here, for example, in this situation of the figure 5, the green sensor on the left will have no overtracks because all its Gaussian components that are in the red areas, they are matched with the red sensors. On the opposite, the red sensor has 2 unmatched components in the intersection areas, and so this sensor has an overtrack of 0.5, which could be considered a abnormal area with our the way we evaluate the trust between two sensors. Shortly, we're using a beta reputation model where we're counting the number of good behaviors and bad behaviors. So good behaviors with equation 5, bad behaviors with equation 6, and then based on these two, you end up with equation 4 with the relative trust between the two modalities. And to decide if things are good behavior or bad behavior, there's an indicator function, which is 1 and when things are going good. When the overtracks are very low, based on the threshold, we also have to tune, and 0 otherwise in the case of a bad behavior. And this model helps to integrate through time. And also there's beta 1 and beta 2 that are forgetting factors, such that if there's no way of comparing the sensors, then the trust goes back to an average value. And as I said before, once we have this distributed trust, so an n by n matrix, we can do some diagnosis by doing some average to obtain some fused trust. Depends which sensor we select to evaluate every sensor. And I also introduce, because we need this in practice, some weights that needs to be context aware. I'm going to talk about this in the next slide. But the end goal is to have some form of threshold on the trust. If the trust is too low, then you had some monitoring alarm to inform the pilot that something is wrong with that ship or with that sensor. And one of the this context aware weights is something we've touched a little bit upon, but is going to be probably challenging in practice. Is the idea that some sensors are better at evaluating the other sensors, and sometimes it depends also on the weather. So, for example, the radar, maritime radars are quite reliable in general, and they're not really tempered by weather. They're hard to attack with a cyber attack. So we evaluate them at being quite good at evaluating other sensors. On the other hand, visual cameras are not very reliable when it comes to tracking objects. And they can easily be tempered by weather conditions, rain, fog, etc., such that we decide them to have a lower value when it comes to evaluating radar or LiDAR, for example. But it's quite hard to be extensive on selecting the weights. So we'll see how we'll have to do with the experimental parts. To illustrate all of this I've presented, here's a small simulation to show the interest in practice. It's a case where we have a ship entering the harbor that is being remotely piloted. There's a bunch of sensors on the ship. There's also a bunch of sensors on the land that will help us cross-evaluate the ship. And we just have two cases, nominal cases, everything is good, and then a case with a spoofing between 200 seconds and 350, just to show the difference between the two. Remember, I showed 3 blocks of diagnostics before. I'm going to show their curve now. First, we're doing a diagnosis where we do the average of the thrust of the land sensor evaluated by the land sensor. This is an auto-evaluation of the land sensor, and we use this to make sure the land sensors are reliable enough such that they can evaluate other sensors. The interest is that most likely the human pilot will have technical control over these sensors if needed, because they are from the harbor or from their company. Second block we're using is the auto-evaluation of the ship. So you evaluate the thrust of the ship by averaging relative thrust of the ship sensor only. Here the interest, so in both cases, there's no alarm being triggered because the thrust is high. It's still consistent even with the spoofing. The interest is more when you have only one sensor that is faulty, because then it's quite fast at detecting a faulty sensor on the ship, because the sensor, they all overlap their field of view. But the third point I was more interested in the scenario is the cross evaluation. You evaluate the reliability of the sensors of the ship with the sensors on the land. And here there's a clear difference between the two scenarios, as the spoofing triggers an alarm in 30 seconds with a low trust with several of its sensors. Right. So to sum up all this presentation, I kind of worked on a framework to detect degraded sensing due to setup faults, adverse weather, or cyber attacks, which are the practical issues we have with this scenario with remote piloting. This framework can help to improve the safety. I'm currently working on real-world data that we have collected. We'll collect more data as well, because I think the deterministic method needs a lot of parameter tuning. But I think as it is quite general and modular, this type of framework and approach could also be implemented to other systems such as group of robots, and also go with underwater sensors.